Hello everyone, I'm Xavier. In this video, I'd like to show you Soul Hunter, an open source multiplayer project I've been developing in Unreal Engine 5.6. The project was created for educational purposes and as a portfolio piece to demonstrate my gameplay programming and multiplayer development skills. Everything you'll see has been built with scalability, networking, and gameplay architecture in mind. Soul Hunter is a competitive multiplayer game where players compete to collect more souls than their opponents before the match ends. The game features three different types of souls: pure souls, fire souls, and frost souls. Pure souls are always visible to every player, while fire souls and frost souls can only be perceived when the corresponding perception ability is active. These abilities are temporarily granted by collecting specific ability tokens scattered throughout the level. This perception system doesn't only affect gameplay, it also plays an important role in networking. As we'll see later, the replication graph only replicates souls that a player is actually able to perceive, reducing unnecessary network traffic while keeping the gameplay fully authoritative. Let's start with the gameplay ability system. The ability system component is initialized in the hunter character and represents the foundation of all gameplay abilities and player attributes. The project currently defines two primary attributes, perception and stamina. Perception is a resource consumed whenever the player activates perception abilities to reveal fire or frost souls, as well as when using his abilities. Stamina, on the other hand, is used for traversal mechanics such as sprinting and climbing, encouraging players to carefully manage their movement throughout the match. The game currently features two combat abilities, Repulsion Orb and Repulsion Shield. Repulsion Orb is a projectile ability. When it hits another player, it launches them in the direction of travel, making it possible to knock opponents off the map and force them to lose valuable points. Repulsion Shield serves both offensive and defensive purposes. It pushes away nearby players and can also block incoming repulsion orbs, allowing skilled players to defend themselves or create space during close encounters. Together, these abilities introduce an additional strategic layer to the game. Success isn't only about collecting souls as quickly as possible, but also about disrupting your opponents and controlling the flow of the match. Now, let's talk about the movement system. The project uses Epic Games' gameplay animation sample as the foundation for its locomotion system. This provides a robust and highly responsive movement framework, allowing me to focus on the gameplay systems built on top of it. The primary customization I've made is adapting the upper body animations to support the repulsion orb ability. While the character is moving, the upper body can independently play the casting animation without affecting the locomotion underneath. The gameplay animation sample has been designed to be easily extensible, so rather than modifying its core traversal logic, I introduced two virtual extension points: can pay traversal cost and pay traversal cost. In the sandbox character, both functions are intentionally left empty. This keeps the sample generic and independent from any specific gameplay implementation. The actual implementation is provided by the Hunter character blueprint, where these functions are integrated with the gameplay ability system and the stamina attribute. Whenever a traversal action is requested, can pay traversal cost is called first to verify that the player has enough stamina. If it returns false, the traversal action is immediately cancelled. If the player has enough stamina, pay traversal cost is executed to consume the required amount before the traversal proceeds. This approach keeps the movement framework reusable while allowing gameplay specific rules to be implemented where they belong without tightly coupling the animation system to the game's mechanics. I would like to briefly explain how input and user interface navigation are handled in Soul Hunter. The project uses Unreal Engine's Common UI as the main framework for input routing across both the menus and the in-game interface. Instead of changing the input mode manually inside the player controller, Common UI manages the active input configuration. This keeps gameplay input, menu navigation, focus, and widget activation synchronized. The project supports two main input methods, mouse and keyboard, and an Xbox compatible controller. Common UI can detect the active device and use the appropriate controller data, making navigation and on screen input prompts consistent for each player. The interface is also organized through common activatable widgets and tagged widget stacks. Screens such as the main menu, tutorial controls, and gameplay widgets can be pushed onto or removed from the correct UI layer, while common UI handles focus and input routing automatically. This approach provides a clean and scalable UI architecture. It avoids duplicated input logic, creates a consistent experience between the front end and gameplay, and makes it easier to add new screens or input actions in the future. Soul Hunter is designed to be playable in multiple languages so players can experience the game in English, Italian, French, or Spanish. The localization system covers more than just menu buttons. It includes the user interface, gameplay messages, tutorial text, subtitles, and even voice-over audio. This means that when a player changes language, the game experience feels consistent across both text and spoken dialogue. English is used as the main reference language. From there, the game provides translated versions for the other supported languages. For example, tutorial instructions, menu prompts, error messages, and dialogue lines can all appear in the player's selected language. The project also supports localized audio. This is especially important for the tutorial, where players can receive guidance through both translated text and voice lines. The goal is to make the game easier to understand and more accessible without forcing every player to rely on English. Another important point is that localization is prepared for real game builds, not only for testing inside the editor. Soul Game includes the supported languages when the game is packaged, so the translations and localized audio are available when players actually run the game. In short, localization in Soul Hunter is about accessibility and polish. It allows players from different regions to understand the interface, follow the tutorial, receive feedback from the game, and enjoy a more complete experience in their own language. It's time to explain how Soul Hunter handles Steam sessions and multiplayer replication. For session creation, discovery, and joining, the project uses the Advanced Sessions plugin. It provides a convenient blueprint layer over Unreal Engine's online session framework and allows Soul Hunter to advertise custom information such as the build identifier, respawn settings, and pickup policy. The actual online backend is Steam Online Subsystem, while Steam Sockets is used as the network driver when the game runs through Steam. During dedicated server development in Unreal Engine 5.6, I also identified and fixed an engine level issue. The Steam game server could authenticate successfully, but online subsystem Steam never updated its session state when the game server connection callback arrived. As a result, the asynchronous session creation task waited forever for a valid connection state and Steam ID. I added the missing game server callback to the Steam Async Task Manager, updated the session interface, stored the server Steam ID, and completed the login delegate. The project also packages the Steam runtime files required by the dedicated server. With these changes in place, the dedicated server now works correctly with Steam in Unreal Engine 5.6. It can authenticate successfully, create and advertise Steam sessions, and accept client connections using the Steam Online subsystem and Steam sockets, providing a complete multiplayer workflow. Finally, let's take a look at Soul Hunter's replication graph architecture. The custom replication graph routes actors into different categories. always relevant actors, dynamic or static spatial grid actors, and souls. Per connection nodes always include essential actors such as the viewer, view target, owning pawn, player state, and relevant streaming level actors. Remote player states are distributed across frames to reduce bandwidth spikes. Souls use a dedicated per connection node. Pure souls are available to every player, while Frost and Ember souls are replicated only when that specific player has the correct perception ability active. This is more secure than replicating every soul and hiding it locally because a client never receives information it is not allowed to perceive. The result is lower bandwidth usage, scalable actor replication, and multiplayer visibility rules that are enforced by the server rather than trusted to the client. To conclude, this presentation has provided a high-level overview of the main systems I designed and developed for Soul Hunter. From the overall gameplay architecture to Steam session creation and discovery, dedicated server support, engine level fixes, and the custom replication graph, every part of the project was designed with scalability, maintainability, performance, and multiplayer fairness in mind. Soul Hunter is not only a gameplay prototype, but also a technical showcase of how multiple Unreal Engine systems can be integrated into a cohesive, production-oriented architecture. Today, I focused on the overall approach and the most important design decisions rather than covering every implementation detail. If you would like to learn more about any of these systems, discuss the technical decisions behind them, or explore other parts of the project, please feel free to contact me. Thank you for your time and for your interest in Soul Hunter.